Okay, everyone, welcome to the first of our fall 2018 virtual combinatorics colloquia. Our speaker today is Vašek Chvátal, who's speaking to us from Prague in the Czech Republic. Vašek recently retired from Concordia University in Montreal, where he held two different Canada research chairs. After completing his PhD with Crispin St. J.A. Nash Williams at the University of Waterloo, one of my favorite places, Vašek taught at McGill University, Stanford University, Université de Montréal, and Rutgers University before going to Concordia. He's a well-known expert in combinatorial optimization, theory of perfect graphs, linear programming, and a number of other areas recently. And one of them is this new problem in Greek topology and metric spaces that he'll talk to us about today. So welcome, Vašek. Thank you very much. I'll hand it over to you.
Thank you. Well, first of all, I want to thank Bill, Martin, and Joe, Alice Monaghan for having invited me to this. I will talk about a problem that I would very much like to see it not solved, that is progress made on. And so I am glad of this opportunity to tell as many smart, talented people as I can about it, in the hope that some of them will take the progress further. And I want to thank them also for introducing this adventure. I mean, this is enormously exciting to me, talking over internet to people on all kinds of continents. I have a bit of a stage fright about the technology. I'm waiting for Murphy's Law to kick in any moment. We'll see if it does. Well, and this is what I'm going to talk about, points and lines. And one of the oldest theorems about points and lines is the Pappus hexagon theorem. Let's see if I can show it. It's illustrated here behind me in the painting. And that is a theorem from the 4th century. And that is a theorem I am not going to talk about. A little more recent theorem from the end of the 19th century originates with a man who gave us matrices. He asked this question, or issued this command, if you want. You can read it yourselves, but won't hurt if I read it too. He asked to prove that no matter how you plop finitely many points in the plane, you will always find two such that the line passing through them contains only those two of your chosen points, unless, of course, they are all on the same line. So he published this question in March 1893, and a solution appeared, which is remarkable for a number of reasons, 3 reasons really. One is how quickly it came. 2 months elapsed before the solution appeared. Then it's remarkably crisp, short. And the 3rd reason is that the H.J. Woodall, ARCS, managed to cram 2 errors into 4 lines. That's an achievement. We don't know if Sylvester had a proof. We do know that the statement is true. It was proved by Gallai, whose name was then still Tibor Gallai, in the 1930s. And this is the theorem, the Sylvester-Gallai theorem, that I will not talk about either. I will talk about its corollary, pointed out by Erdős or observed by Erdős. And this is really a fairly immediate corollary. To deduce it from Sylvester-Gallai, you look at your points which do not lie on a single line. Gallai assures you that two of them will determine a line which doesn't pass through a thread line. So take them, rip one of them off, concentrate on the remaining n-1, and by induction, either they determine at least n-1 lines, in which case this green line that you see here, this green line, is an extra line because it doesn't pass through any of the points in the oval, right? Any of these. So in that case, you are done. You have got your n lines. The only other possibility is that these n-1 points lie on a single line, in which case you have this sort of configuration known as near pencil, and that has got n points, n lines. By the way, if you go over the proof, you can also deduce that the near pencil is the only optimizer, the only configuration which will have precisely n lines. Right. So that is my starting point. I don't know if you can see the top of the screen. I cannot, but well. So this theorem, people often and erroneously refer to as the Bruijn-Erdős theorem, and the reason is that the Bruijn-Erdős proved a theorem which generalizes the hell out of this geometric theorem. The combinatorial generalization goes like this. Nothing to do with geometry, really. Your set E is capital E, is the family of your lines. The only thing you want from them is that none of them is the whole thing. None of them contains all endpoints, and every two distinct points belong to precisely one line, which is U in the geometry case. Well, and then the same conclusion holds, and among the minimizers, there is a near pencil as before, but a new one appears. Because now you also have access in this more abstract combinatorial setting, you also have access to finite projective planes, right? And a finite projective plane has all the family of its lines has all the properties required of E, and the size of E equals the size of V. So it's a sin to call the theorem in the red frame at the top of the screen, this one, Bruijn-Erdős theorem. And I apologize that I have been committing that sin myself. I didn't know any better then. Well, that's it. I will not apologize any further, but it's a heartfelt apology. Other people do it too. And this is, by the way, the reference, 1948. And as we have seen, the Bruijn-Erdős theorem is a far-reaching generalization. The statement in the red frame is just the tip of an iceberg. And here is a question that motivates, that is central to my talk now. And a possible answer is here. My friend Xiaomin, whom you could have seen a moment ago, who is watching this from Shanghai, and I asked this question. And to make sense out of the question, I have to tell you what we mean by lines in a metric space, right? And this is what we mean. When you think of a line in the plane, line AB really consists of 5 parts, A and B, and everybody to the left of A, everybody in between A and B, and everybody to the right of that. And these properties of X, Y, Z can be stated in terms of distances. There are only, I said there are 5 parts to the line. Here there are only 3. But the thing is that A can qualify for both X and Y, and B can qualify for both Y and Z. So lines in the Euclidean plane can be defined in terms of distances. Well, you can take the same definition and apply it to an arbitrary metric space. And that's how Xiaomin and I define lines. They may look at it a little different, but again, they consist of A, B, all the points X like this, all the points Y like this, all the points Z like this. And those lines in the metric spaces may look nothing like the familiar lines in the Euclidean plane. In France, you see often at railroad crossings this sign, this warning, and in case your French is not up to scratch, this says one train can hide another. Watch out when you are crossing. Behind the train, you see there can be another. The same warning applies to lines in metric spaces. Here is an example. Here is a nice, lovely metric space. 5 points, and the distances are the usual graph distances, which in this particular case means adjacent points at distance 1, non-adjacent points at distance 2. So what is line AB? Well, nobody can play the role of Y. Nobody's in between A and B. But point E, this one, can play the role of X, plays the role of X. Right? The distance from A to E plus A to B is distance E to B. So E to A plus A to B is E to B. Similarly, C can play the role of Z. So the line is EABC. When you look at AC, well, no, there is only B is between A and C. And nobody plays the role of these outliers, X or Z. So you see, one line is a proper subset of another. That's not what we are using. So here's our question. It's really a conjecture, right? We conjecture that the answer is true. The different people have different attitudes to the conjecture, right? Some people, when they conjecture something, it really means they stake their honor on the truth of the statement. My doctoral advisor, whom Bill mentioned, Crispin, St. John, Alva, Nash-Williams, he went so far that he coined the term, possible conjecture for conjectures, for conjectures that he didn't quite want to stake his honor on. I don't have those forms normally. Let's say about my honor the better, maybe. But I mean, when I say something, when I conjecture something, it really means, wouldn't it be interesting if it were true? And I would like to know, right? But even with this attitude, somehow I wimped out. I don't know why. When Xiaomin and I were writing this paper, I stated the question as a question, and not as a conjecture. In this talk, I may flip between the two forms, which really are equivalent, right? So maybe I should go back. George Polya taught us, or tried to teach us, or advised us to how to deal with difficult problems. And one of his pieces of advice is, if you have a problem that you cannot solve, try to come up with an easier problem that you can solve. And in the best tradition of following on that advice, Ida Cantor and Balázs Patkos proved the conjecture in a special case. Now, again, to make sense out of this statement, I have to tell you what the blue terms mean. Well, non-degenerate means no 2 points on the same horizontal, vertical, no 2 points on the same horizontal. You have a finite set of points in this sort of general position that's non-degenerate. And Manhattan lines, well, that's the hoi polloi term for what we, the professionals, call lines in the L1 metric. Right? That term comes from the fallacy that houses in Manhattan are laid out on a rectangular grid, so that when you want to walk from point A to point B, you have to walk all the time on either the, say, north-south line or east-west line. That, of course, that fallacy is completely erroneous. There is Broadway, which ruins it. There is Greenwich Village, where all hell breaks loose. But, I mean, saying Manhattan minus Broadway and minus Greenwich Village would be a mouthful. So we will not nitpick, stick with that. So Manhattan distance. What are the lines in the Manhattan distance? Well, when you have A and B like this, I said to walk from A to B, you can walk any way you want, as long as you walk north or east all the time. So all these points can play the role of Y. And similarly, here are the possible X's, here are the possible Z's, the two infinite quadrants. Okay. Now.
See ya.
Yes?
Okay, I'm going out.
So, is somebody talking to me? No.
Sorry, Vašek, I'll mute people.
You just muted him.
I hope not. I'm unmuted by voice. Lovely, great, fine. So, the picture I just showed you is a picture of a Manhattan line in case there is no degeneracy. Right? So those are typical Manhattan lines. If your group is degenerate, if you hobnob with people who live on the same avenue, on the same street, then lines will look a bit different, a lot different, right? The X and Z, rather than being quadrants, will be half planes. So this is a hint for why Ida and Balázs need the non-degeneracy assumption. Right. Well, still that assumption is a bit of a thorn in our collective side. It would be nice to prove it without it. Well, in their paper, they also have partial result for general, degenerate, even including degenerate cases. Not quite N, but linear. That's 6 years ago. Now Ida kept working on it on her own, and just a few weeks ago, she improved the 37 here to 2. To 2. Well, here. Yeah, so let's see how small the denominator will get in the future. So this is one special case where we know the answer. Here is another special case. Right. Not, well, judge for yourself what you think of it. Well, Porya's precept, his advice, to look for an easier problem that you can solve, can be turned around and sort of dualized. You can also say, look for an easier problem that you still cannot solve. Look for a problem that is just beyond your capabilities, but just. And well, that may provoke you into rising to that challenge. And once you solve the problem that you couldn't solve before, well, you learn something and progress is being made. So what would the dual precept say here? Well, look at cases when the spectrum of non-zero distances is smaller, not just 2, but say 3 to begin with. So distances 1, 3, and 7 would be uninteresting, right? Because you would have no triples of points where B is between A and C. A more interesting case would be 1, 2, and 4. Is it true when all non-zero distances are 1, 2, and 4? As far as I know, nobody looked into this. Another interesting case is when all the non-zero distances are 1, 2, or 3. People did look into this and didn't quite prove it there, but have a partial result. By the way, of course, these two lower bounds, n over 15 and omega of n to 4 over 3, are incomparable. Doesn't really need to be emphasized, but it may not hurt to emphasize. Right, the asymptotic bound, of course, grows much faster than the linear bound, but being asymptotic, it kicks in from some n. So there is a point to quote in both. Now, another partial answer that we know, and more generally, you could look at metric spaces which are defined by graphs with a normal graph distance. Those are easily visualized. That's their appeal. We don't know that the answer is true for all graphs, but here was an example of a class of graphs where the answer is true, where the conjecture holds true, if you want. And again, I have to explain the undefined term, bisplit graph. Bisplit graphs are 3 colorable graphs, say the colors red, white, and blue, where every red vertex is joined to every white vertex. Right, so that's the definition of bisplit graph. And there are 5 authors here because Xiaomin and Esan proved this independently of the other 3. So, and that's a fairly recent result. So what would the dual Porya precept say here? Well, what is a slightly more difficult problem? Well, all these bisplit graphs are comparability graphs, right? Meaning, we all know, just in case somebody doesn't know what's a comparability graph, means we can assign arrows to edges in such a way that every two arrows in a series complete to a transitive triangle. And here's the assignment is clear. You orient all edges from left to right. So the only way you can get two edges in series would be go from here to here and from here to here. But then, of course, that completes the transitive triangle. So prove this for compatibility graphs. That would be the next challenge. And by the way, I will be saying the Bruijn-Erdős property for the obvious thing, which is either, no, not either. There are at least indistinct lines, or there is a line consisting of all endpoints. Just terminology, the Bruijn-Erdős property. Here is another class of graphs, and slightly older result, where we know the answer is true. Chordal graphs, right? Also known as triangulated or rigid circuit. Every side has a chord. So, right. So that's a class of graphs. What challenges does this result suggest? Well, all these graphs are household domino free. House is a complement of P5, right? There's a square with a triangle on top. Whole in this context means any cycle with like offlines chordless cycle of length at least 5. Some people also mean length 4. That's not the case here. So whole chordless cycle of length at least 5. And domino is a hexagon with a long chord, with a single long chord. Or if you want, two squares glued together along an edge, right? So household domino free graphs are a proper superclass of these graphs, right? So obvious challenge, prove the conjecture for those. And this result, in fact, introduces a common theme of making up classes of graphs from prescribed building blocks by prescribed operations, right? So in this case, the question which suggests itself is, do substitutions in general preserve the Bruijn-Erdős property? If you have two graphs with a Bruijn-Erdős property and substitute one for a vertex in another, do you get another nice graph, well-behaved graph? Well, we don't know, and we don't know even in the simplest cases of substitution, which are substituted in a graph with two vertices, right? Which means making twins. You don't know what happens when you split a vertex into non-adjacent twins. You don't know what happens when you split into adjacent twins. And the other operation, well, there is not much to say there. We don't know whether that operation preserves the Bruijn-Erdős property either. So, and when we are on this result, I will digress a bit, because the authors of this result made a stronger conjecture than the conjecture made by Xiaomin and myself. And to explain that, I need a couple of terms, couple of symbols for notation. The terms are universal line, that means a line which consists of all the points, and mighty pair is a pair of points that determines a universal line. Universal line is a term which is universally used. Mighty pairs I chose deviously for alliteration because I want to denote lambda, the number of lines, and mu, the number of mighty pairs. And Abulkar and company, sorry, before you get there, in these terms, lambda and mu, the conjecture by Schaumann and myself says this, right? Either there are at least n lines, or there is a okay, there are at least n lines, or otherwise there is a universal line. Now that conjecture is in a way ugly, right? Because it's a logical disjunction of two predicates which have nothing to do with each other, right? It's either one extreme or the other. The Abulkar, Matamala and company, etc. conjecture interpolates between those two extremes. This is what it says. Right? I mean, the bottom predicate implies the top predicate, but not the other way around. So that's a stronger conjecture than our conjecture, but in a way prettier. And you know, sometimes stronger conjectures are easier to prove. For instance, if you go by induction, although I don't see what role induction, how you could get foothold for induction here. And Abulkar and company proved, actually, it is a theorem that we had before on the previous slide. They proved a stronger theorem. They proved not just our conjecture, but the red conjecture. So digression over. Well, how else could we follow Polya's advice? So far, I've been reviewing results where you prove the conjecture for special metric spaces. You could also say, let's prove as a weaker statement for all metric spaces, right? Rather than proving that without a universal line, you have to have at least n lines, let's prove that without a universal line, you have a number of lines which rose to infinity, right? And here is a theorem in that vein, the best we know, square root of n order of magnitude. And when you go to graphs, you can do better. Now, 4/7 is more than 1/2, right? So, and while we are on the subject of graphs, as I said, we don't know whether or not our conjecture is true for even in the case of graphs. There is also another conjecture about graphs. And here we are again in the situation I commented on a while ago, which is you have two conjectured lower bounds. This one grows asymptotically farther, asymptotically faster than that one, but again it kicks in only for big N. Now both of these conjectures are true for special graphs that we have seen. Examples, here is a very easy exercise. When you look at complete multi-party graphs, they satisfy both blue conjectures above them. So they are not completely hopeless, completely absurd. Again, one might say it's a pity that they are, well, not, that we can't interpolate between them. And in fact, we can. Here is a conjecture. Right? The conjecture is that, well, what it says. The conjecture is that if you want to minimize the number of lines in a graph with no universal line, the best you can do is a complete multipartite graph. And that conjecture titillates me no end. Because, you see, in this top blue conjecture, the lower bound n really was inherited from the general metric spaces conjecture, where, of course, it cannot be improved, right? Near pencil. Right? In near pencil, you have got this n, sorry, I'm pointing to the wrong n. This n cannot be improved near pencil. But it looks like for graphs, something completely else is going on, completely different is going on. It looks like the right order of magnitude is n2/3/2. That we are dealing with completely different animals here. We are in a completely different context. Somehow the original conjecture, inspired by what people call the Bruijn-Erdős theorem, was just a red herring, this n. For graphs, something completely different is going on. Well, that's what really titillates me a lot. And this is what Jore knows, and we know because he told us. And the interesting thing, one interesting thing is that the complete multipartite graphs are not the only minimizers. Right? The complement of the Peterson graph is also as the smallest number of lines, which goes to show that if you wanted to prove that conjecture, you might have a little harder time because, well, the complete multipartites are not the only minimizers. Well, still on the subject of graphs, we know that lines in metric spaces can be exotic. Xiaomin and his friends proved that in almost all graphs, they are not exotic in this sense. A line cannot hide another in almost all graphs. But, well, exotic. What we are used to in Euclidean space or Euclidean plane is more than this statement. We are used to lines which have a stronger property. Every two lines meet in at most one point. So these authors also asked themselves, when are the graphs really mundane in the sense that every two lines meet in at most one vertex? Well, just to keep the suspense a little longer, one way that lines can be mundane is that each of them has only 2 points. Right? And that happens for complete graphs. So complete graphs pass here. Another possible reason why the top property is held is that there is only one line. Every line is universal. Well, the path has it. Right? In the path, every 2 points determine the whole thing. And apart from the path, and that's easy to prove, there is also the C4, the cycle with 4 vertices, or chordless cycle with 4 vertices. Right? Every 2 points determine the whole thing. Well, the theorem says that that's the only way the graphs can be mundane. And we don't really know what the families of lines look like. Right? We conjecture that, well, I mean, the family of lines is a hypergraph in a metric space or in a graph. And we conjecture that either there are plenty of those, meaning at least n, or one of those hyper edges of the hypergraph is the whole thing. How difficult it is to recognize such hypergraphs? We don't know. We don't know it for metric spaces, we don't know it for graphs. It's annoying. By the way, the red question and the blue question are different questions. Here is an example which we will not delve into. Lines in a metric space which cannot be represented by graph. Right. A related question is also this. You can, whenever you have metric space, you have a partition of the X set of the complete graph on that underlying set. Well, equivalence relation, if you want. Two edges belong to the same block if and only if they determine the same line. We don't understand those relations, right? Here is an example. We will not check the details, but I mean, one partition, another graph, another partition. We don't know how to recognize those. If they give me a partition and ask me to find out whether or not it comes from a metric space or a graph, I won't be able to do it in polynomial time. So how difficult is that? Here is an example of a partition which is not representable. It's so small that you can justify the answer by brute force, but there are bigger examples of the same phenomenon. And even here, I mean, I don't know any, for this particular partition, I don't know any neat, elegant argument which shows that doesn't come from a metric space. Yeah. And I have been talking about special cases of the conjecture, restricting the conjecture. Now let me go in the other direction. How could we generalize it? Well, here is a key to the generalization. We can restate the definition of the line, and we say it more simply. A line in a metric space consists of AB and all the points such that the 3 points ABC, one of them is between the other two. Right. So really, when we talk about lines in a metric space, we can access the metric space. It's enough to access the metric space through this 3 uniform hypergraph. Right? Let me call this hypergraph metric. Right? So now we can define lines in an arbitrary hypergraph, 3 uniform hypergraph, not just the metric ones, not just the metric hypergraphs. Now, so our conjecture says that in every metric hypergraph, you have got at least n lines, unless you have got a universal line. Now, what's the point of insist on metric? Wouldn't it be true if for an arbitrary 3 uniform hypergraph? And here the answer is resoundingly not. Schaumann and I have a construction which shows that even without the universal line, the number of lines can grow more slowly than any power. It's also true that it will grow to infinity, but we can't do anything better than log n. And we can't do even anything better than this coefficient 2, right? We can't even get rid of the little of 1. But that's taking us far afield. These hypergraphs from the construction are, of course, not metric, right? Because if one of them was, then they would be counterexample to the Vašek Chvátal conjecture. And we know that I mean, we have infinitely many of them, and we know that none of them is metric because all of them contain a small piece, small induced subhypergraph, which is not metric. That's how we know. This is a question we don't know the answer to. We have got, I think, 3 or 4 examples of non-metric hypergraphs, which are minimal in the sense that all induced subhypergraphs are metric. The Fano hypergraph is not metric. We have 2 proofs of this fact, one by myself and one by Xiaomin. The one by myself is really ugly, brute force, disgusting. The one by Xiaomin is very neat and elegant, and it relies on a different theorem also by Xiaomin, which is far from trivial. Right? So, and here is a question I would like to close with, because even if you don't care about lines in metric spaces, even if you find them contrived, I think the notion of metric hypergraphs is easier to accept as interesting basic, right? In a metric space, you list all triples of points such that one is between the other 2. Well, that's a fairly basic invariant of a metric space. We have no idea what they look like. We don't know how to recognize them. And that's pretty much the question I would like to end with, except not quite. But everything that I said here and more will come out soon in this book as chapter 13, whose title is completely misleading because I am talking about the possibility of the Bruijn-Erdős theorem in metric spaces. Being an opportunist, I put that like this because the collection was about graph theory conjectures. So that's it, and thank you for your attention. I'm done talking.
Thank you very much, Vašek. So let's allow people to raise their hands and ask questions. And if you have a question for Vašek, please click the raise hand. I'm unmuting you as we go along. Yes, there we go. So do we have questions? Maybe you just speak up. Oh, okay. So people keep themselves muted. So we're handling questions here. So I have a simple question for Vašek as we get started. So Vašek, if I take the metric space of the unit sphere, and A and B are the North Pole and South Pole, what is the line joining A and B?
The whole sphere.
The entire sphere. Okay.
The whole sphere, the entire sphere.
Okay.
So that will not be a counterexample to our conjecture.
Okay.
Great job, Vašek.
Thank you very much, Vašek.
Yeah, thank you.
Okay. So the only question I saw was from UMass, and that was from Sarah Marie. Are there other questions?
Can you hear me?
Yes, we hear you.
Vašek, Peter Winkler here. How are you?
Hi.
Hi, Peter.
A question. So another natural definition of a line in a metric space.
You might want to turn your microphone off, your speaker off, Peter.
Yeah.
Speaker off. Is that better?
Yes.
I heard Tiny yes. Okay. Vašek,
Yes.
another natural definition of a line in a metric space might be a set of points of which no three determine a triangle. Of course, if you have that definition, you lose the property that 2 points determine a line uniquely. And probably most of the questions you've asked become trivial one way or the other. But maybe there's some other questions that are quite interesting for that definition of a line, which looks maybe more like a line than your definition.
I love you. This is, I couldn't have asked for a better question than this. I'm going to go back up. That, just a sec. No. I will explain in a moment why I love you. Yeah. Let's look at your definition, your line. Schauman and I call your line a closure line. Closure line, because we think of it in terms of closure. Right, to start by, when you want to construct closure line AB.
Could I ask you to repeat Peter's definition?
When you, the definition is this, closure line AB, it's a bit complicated. You get by starting with AB and the normal line AB. Then if in that normal line A.
Fully understand what above and what you're erasing.
Or Murphy's law does kick in.
Bill, you're muted if you're saying anything.
I apologize. As I try to mute participants, the list of participants gets randomly permuted.
Okay. I absolutely insist on answering that last question because you will see why. So closure line is defined like this. It's the smallest set which contains the normal line AB, and with every 2 points xy, distinct points xy, it also contains the normal line xy. Right, so you can think of it in terms of recruitment. You start with a normal line and then you co-opt other points in case you find a point outside what you have, which is in between, which forms which is in between two other points that you do have. Great, fine. Now, in terms of closure line, you see, in terms of normal lines, Sylvester-Gallai theorem does not hold in this metric space, right? Because, right, Sylvester-Gallai theorem would say either there is a universal line or there is a 2-point line, but that's not the case here. Every line has 4 points or 3 points, and the whole thing is 5 points. So Sylvester-Gallai theorem does not hold in terms of normal lines. However, if you switch to closure lines, things look much better suddenly, because every closure line is universal, right? When you start with, say, AB, you get EABC, and then ENA, have you co-op D. Every closure line is universal. So when I made that observation way back, I formulated a conjecture which says that Sylvester-Gallai theorem holds in metric spaces with closure lines. Now, I battled that conjecture for about 5 years, some very smart people thought about it. Somebody, a luminary at Princeton, gave me a counterexample during my talk. Then we found out it was not a counterexample during my talk. So after the talk, he gave me another counterexample privately. That was also not a counterexample. So anyway, it was a non-trivial conjecture. And after, I don't remember how many years, maybe 4 years, Xiaomin proved it. Xiaomin Chen. And that's a lovely proof, yes. If you go, I mean, if you are interested and look up my paper in that collection that I had on the last slide, the proof is there, a sketch of the proof. And when I said the fact that the Fano plane is not a metric hypergraph, well, that follows from Xiaomin's theorem, right? Because in Fano plane, every closure line has precisely 3 points. So Sylvester-Gallai theorem does not hold there. So it cannot be a metric space, metric hypergraph. I'm done talking. And thank you for the question.
Nan has a question.
Hi, Vašek. I have a quick question. If a metric space has the Sylvester-Gallai property, does it automatically have the Bruijn-Erdős property?
I don't think so. But, well, we think every metric space has a Bruijn-Erdős property, right? So if our conjecture is true, then the answer is yes. But there is no easy there is I don't see any easy argument that would show that the Sylvester-Gallai implies. I don't know. I would have to think about it. But good question. Thank you.
Any more questions? Do we have any more questions? Well, I think that that we'll finish up by thanking Vašek.
I have a problem where obviously it's an 8 a.m. I'm dead tired. I walk in.
Yeah,
And
you guys are.
I'm going to just mute that. Okay. Okay. So who's okay? The muting and unmuting task is non-trivial. So thank you everybody for attending, and we'll terminate the session here. And stay tuned. November 14th, we'll have Vic Reiner speaking on cyclic sieving, and that will be hosted by St. Michael's College. So thanks again for attending. We're going to terminate here.